Welcome back to the Deep Dive, the place where we turn massive amounts of source material into actionable, fascinating knowledge. Today, we are tackling, I think, the single biggest, most frustrating bottleneck for any ambitious large language model agent, and that is memory. I mean, specifically, that fundamental limitation of the finite context window.
Yeah.
You know the phenomenon, we've all seen it. Some people call it digital amnesia. You give an LLM agent a task that needs a long runway, say 50 turns of complex configuration, and by the end, it's completely forgotten the crucial instructions it got on turn one.
Exactly. It's like it's brilliant for a moment, but it just keeps bumping into the wall of its own memory capacity. That specific hurdle is what our sources are really digging into today.
So to really get a handle on the solution they're proposing, we first have to break down the problem. It's really a dual nature thing, isn't it?
It is. It's a lot like human cognition, actually. You're dealing with two distinct systems. First, you've got your short-term memory, or STM. For an LLM agent, that's all the active information sitting right there in the current input context. The conversation history, the immediate prompts, it's, absolutely crucial for what's happening right now.
The immediate decision.
Precisely. And then you have long-term memory, or LTM, and this is the persistent accumulated knowledge. You can think of it like a knowledge base or a vector store.
So this is where it would keep things like user preferences or facts it learned from past tasks.
Exactly that. LTM is what allows an agent to actually learn over time, to build a kind of identity across sessions.
And that brings us to the core idea from our sources today. It's a unified end-to-end framework they call AgeMem. That's agentic memory. And its whole mission is to solve what they call a fragmentation problem. So instead of these two memory systems being like separate modules you have to constantly babysit,
Right.
AgeMem integrates LTM and STM management directly into the agent's own decision-making policy. It's trying to build an integrated brain, not just a bunch of disconnected storage drives.
And that's the key distinction. The so what here is really how current systems work. They treat LTM and STM as totally separate, loosely coupled things.
So they don't talk to each other very well.
Not really, no. You often see these architectures where the short-term memory, the STM, is just static. It just passively soaks up tokens until it overflows.
And then what?
And then some LTM manager, often a totally separate model, gets triggered by some heuristic rule to retrieve or store information.
So it's all based on guesswork, like preset rules.
Exactly. Rules like retrieve every 5 turns or summarize when the context hits 80% capacity. And because this management is happening outside the agent's main reasoning loop, it's just suboptimal by nature. It leads to noise, inefficiency, you name it.
AgeMem is aiming for something end-to-end optimized, where managing memory is just another decision the agent makes for itself. Let's unpack some of those historical failures because people have been trying to solve this memory problem for a while. Why did those older modular approaches keep filing short?
Well, if we look at the attempts to just enhance the STM, that immediate context window, the standard trick was always retrieval augmented generation, or RAG.
RAG.
And RAG is useful, for sure, but it doesn't solve the problem of context noise. I think of RAG less as smart memory and more like an overeager librarian who just throws every single book related to your query onto your desk, whether you need it or not.
So you end up with a ton of irrelevant information cluttering up your active context, and you still haven't fixed the core problem, which is context explosion. You're just hitting that token limit even faster.
Exactly. And the NTM side was just as rigid. Those older systems often relied on these auxiliary agents, basically a specialized memory manager LLM whose only job was to decide what to do.
Which just sounds complicated.
It added massive system complexity, and it just lacked any real adaptability because, again, the management was happening outside the main flow of thought.
So to unify all of this, AgeMem had to overcome 3 big hurdles. What was the first one, the first big technical challenge?
The first one they call functional heterogeneity coordination.
Okay, that's a mouthful.
It is, but it's a fancy way of saying we need LTM and STM to stop fighting each other and actually work together. LTM operations are about persistent stuff, what to store long-term, what to discard.
Right.
But STM operations are immediate. They're about what to retrieve right now, or what to summarize, or even what to just remove from the active window. These are fundamentally different jobs, and training one single policy to handle both is incredibly hard.
It sounds like trying to teach a chef how to handle both the grocery ordering for the week and the immediate temperature of the frying pan at the exact same time.
That is a perfect analogy. Then the second challenge, C2, was the training paradigm mismatch.
Okay.
Standard reinforcement learning, RL, it assumes this, continuous journey with stable rewards over time. But memory operations aren't like that. Suddenly deciding to summarize 30 turns of conversation or delete an old fact, these are fragmented, disruptive
They
actions.
break the flow.
They completely break the flow. It makes end-to-end optimization a nightmare when your policy keeps hitting these sudden reset buttons.
And the final one, C3, was more about just practical deployment, right?
Yes, practical deployment constraints. If you have to rely on a whole other expert LLM just to manage memory, which old systems did, you are dramatically increasing your inference cost, your latency. AgeMem needed to bake this control directly into the main agent itself to make it cheap and fast.
Okay, so let's get into the solution.
Mm-hmm.
AgeMan basically brings it all in-house by giving the agent total agency. This is the core innovation, right? They expose memory operations as tool-based actions.
That's it. The LLM agent itself autonomously decides what memory operations to perform and, crucially, when to perform them. It turns the LLM into its own memory surgeon.
And that tool-based interface is the engine for the whole framework.
It really is. The agent gets equipped with 6 specific tools, all very clearly categorized, to get this fine-grained control. It makes memory management a choice, not, some external command.
Let's go through them. What are the LTM tools?
So the LTM tools modify that persistent knowledge base. You have ADD for storing new relevant info. You have update to modify entries when facts change. And you have delete to get rid of obsolete or just wrong knowledge.
So it's about proactive maintenance. It's not just piling up junk forever.
Exactly. And then for the STM tools, which control that immediate active context, you get real precision.
What are those?
You have retrieve, which intelligently pulls stuff from LTM into the current context. You get summary, which can compress long conversations into just a few concise tokens. And you have filter.
I love that one.
Yeah.
The agent can actually decide to filter context. That's such a huge step up from RAG just dumping information in.
Absolutely. And here's the thing. Using these tools is mandatory. It's built right into the agent's policy flow.
What does that workflow look like?
The agent has to follow a structure. First, a think block where it has to articulate its reasoning and plan its next step. Then, if needed, a tool call block to actually do the memory action. And only then does it produce the final answer.
So memory management isn't a side quest anymore. It's a required step in the reasoning process.
It's part of the core loop.
Which brings us right back to that training problem, C2. You've given the agent all these powerful levers, but how do you teach it to use them effectively when the rewards for those actions are so, sparse and fragmented?
That's where they came up with this really ingenious 3-stage progressive RL strategy. Instead of trying to optimize the entire policy at once, which is nearly impossible, they break the learning into these logical chunks.
One piece at a time.
One piece at a time. And they pair it with a specialized optimization method designed to handle those sudden jumps in experience that memory actions create.
So what are the stages?
You can think of it like human cognitive development. Stage 1 is LTM construction. The agent just has casual contextual interactions. Its only goal here is to learn how to spot salient info and use the LTM tools ADD and UPdate to store it correctly for later. This is the agent learning basic facts.
And then stage 2.
Stage 2 is STM control under distractors. This part is fascinating. They explicitly reset the short-term context, so the agent gets temporary amnesia about the immediate conversation.
But the LTM from stage 1 is still there.
The LTM persists, and then they deliberately throw a bunch of irrelevant, distracting content at it. The goal is to force the agent to learn proactive STM control using filter and summary to suppress all that noise.
So stage 2 is basically a distraction test. Can you stay focused?
Precisely. And only after that do you get to stage 3, integrated coordination. The final multi-step query arrives. And now the agent has to coordinate retrieval from its LTM, the knowledge it stored in stage 1, with the active STM management it learned in stage 2 to produce the final answer.
So to steer all of that learning, the reward system has to be pretty sophisticated. It can't just be about getting the final answer right. It has to reward smart behavior.
Oh, absolutely. It has to incentivize the agent to be like a digital economist. The total score is a weighted sum of 3 major parts. The simplest is just accuracy on the final answer.
But the really clever part is rewarding the process itself.
Correct. The next component is a reward for context management. This is all about resource efficiency in the STM. It rewards the agent for using fewer tokens, for summarizing before the context overflows, and it heavily penalizes it if it accidentally loses critical info.
So it's teaching the agent to be proactive and frugal.
Yep. And then the final piece is the reward for memory management. This is what incentivizes storing high-quality, reusable knowledge in the LTM. It measures the quality of what's stored. Are these facts actually useful later? And it actively rewards meaningful update or delete operations.
So it's not just learning to remember, it's learning to forget gracefully and keep its knowledge base clean.
That's the goal.
So after all that complex training and policy optimization, what did this actually deliver? Did it work in the real world?
The results were consistently strong. Across 5 different long-horizon benchmarks, AgeMem got the highest average performance on both of the LLM backbones they tested. On the bigger Qwen 3 model, they saw relative performance gains of up to 23.52% over the basic no-memory baselines.
Wow, that's a huge lift just for managing its own information better.
It's a massive lift, and crucially, the RL training itself wasn't just, icing on the cake.
It really mattered.
It really mattered. The Bay reinforcement learning provided a significant, measurable jump in performance, almost 9 percentage points, over the version where they just gave the agent the tools but didn't train it how to use them strategically.
And I love this idea that the system rewards quality over just quantity of memory. Did that actually work? Did the agent learn to be selective?
Yes, and that was one of the clearest results. The memory quality, or MQ score, that AgeMem achieved was the highest of all the methods they compared it to. So it validates that this unified rewarded approach really does promote storing high-quality reusable knowledge, not just, every random thing it sees.
And what about efficiency? Did the STM tools actually cut down on token waste compared to the old RAG systems?
They absolutely did. AgeMem showed really significant efficiency gains. On that Qwen 3 model, it achieved a 5.1% reduction in prompt token usage compared to its RAG counterpart.
And that 5% is the proof that it actually learned to compress and filter intelligently.
Exactly. It's the economist agent concept validated. It saved computational resources by being smart.
I think the real power of this comes to life when you look at the case studies. Let's start with case 1, the one focused on LTM maintenance, where the agent has to manage personalization over a long chat history.
Right. So the scenario starts with a user saying they're a visual learner and they prefer 60-minute study sessions. The trained AgeMem agent immediately uses the ADDI memory tool, stores those preferences, pretty standard.
But then things change.
Right. The conversation goes on, and later the user changes their mind. They say 60 minutes is too short. They actually want 120 minutes now. The agent recognizes the stored fact is now inaccurate, so it strategically uses update memory to modify that entry.
Okay, that makes sense. But this is where the advanced strategy kicks in, right? The part driven by that memory management reward.
This is it. Much later, the user confirms the 120-minute preference is permanent. The agent then realizes that the current memory entry, while updated, still contains what it calls an obsolete historical reference, the old 60-minute preference. It's like technical debt in its own brain.
So what does it do?
It executes this really smart cleanup operation. It uses delete memory to get rid of the entire entry with the old reference, and then immediately follows up with a fresh ADDI memory call containing only the confirmed current 120-minute preference.
Wow. So it's actively curating its own knowledge base to keep it pristine.
Yeah.
That's far beyond just basic accumulation. It's editing its own history for efficiency.
It is genuinely impressive. It's the agent proactively managing its own internal consistency.
Let's look at case 2, the one showing the STM management. This was the focus of that stage 2 training with all the distractions.
Yeah, this is a great demonstration of focus. The user is trying to plan a machine learning course, but then they just drift off into totally unrelated hobbies. They start talking about quantum computing, then baking sourdough bread, then latte art techniques.
And the old baseline LLM would have just politely absorbed all of that, right? It would have polluted its context window with notes on sourdough starter.
100%. But the trained AgeMem agent immediately uses the filter context tool. It just removes those irrelevant topics, the sourdough, the quantum computing, the latte art, and maintains this laser focus on the ML course planning. It suppresses the noise before it can interfere.
So no more wasting valuable context space trying to figure out how to fold dough and analyze eigenvectors at the same time.
Thankfully, no.
Yeah.
And then later, as the agent develops a really detailed schedule, the context starts growing fast. Before it even hits the max token limit and gets a penalty, the agent proactively uses summary context to compress that whole schedule down into a compact representation.
It's real-time resource management, all done autonomously.
That's it.
So this whole framework, AgeMem, it feels like the successful culmination of this push for unified agent-centric memory. It's replacing all those rigid reactive heuristics with a single end-to-end optimized policy. The results seem to show it's more consistent, more efficient, and more personalized.
It genuinely feels like we're watching LLM agents get a kind of nervous system upgrade, one that handles both long-term storage and immediate attention span.
A huge step forward.
It truly is a step toward profound cognitive autonomy. Now, the researchers do acknowledge that while these 6 tools are highly effective, the current toolset is fixed. So the immediate next step is to explore, how to extend that for even more fine-grained, maybe even customized control over memory.
Which leaves us with a fascinating final thought.
It does, and it's a question for you, for the listener. If the agent can already decide when to update or even delete its own memories based on a learned policy, what's the next layer of cognitive autonomy? What's the next capability these agents will need to truly start mimicking human long-term reasoning?